Tell me what one of the chemical properties of ammonia is. One of the chemical properties of ammonia is weak base. Weak base is hydrolyzed water. And so when I think about ammonia, I think, oh, it can neutralize acids. But when I think about ammonia as a weak base, hydrolyzing water, then I think about it as a precipitating agent. There are lots of insoluble hydroxides. And so if ammonia let's say ammonia hydrolyzes water and produces a little bit of hydroxide, a little bit of hydroxide can cause precipitation of metal ions. For example, iron 3. Is iron 3 hydroxide soluble or insoluble? Iron 3 hydroxide. Hydroxides are insoluble except for group 1, ammonium, calcium, strontium, and barium. Good. And so iron 3 hydroxide should be insoluble precipitate. So immediately when I think about ammonia, I think I'm going to get an iron precipitate hydroxide. And just what you do is you think in terms of the magnesium nitrate problem we just did the other day. Remember magnesium nitrate? And so when I think about iron 3 sulfate, it's the same thing. I'm going to get iron 3 sulfate plus aqueous ammonia is going to give me iron 3 hydroxide and ammonium sulfate. Okay. And so use magnesium nitrate as a template, and then try to figure out the iron 3 sulfate. So I did partially for you, but not completely. I want you to finish it. Okay. What else can ammonia do? Well, ammonia can. Does ammonia burn? Can you combust ammonia? Yeah, it does. And so ammonia can undergo redox reactions. It not only can burn, but it can do other things. Redox can. We'll talk a little bit about that today. Redox. And so I think of ammonia as having redox properties, acid-base properties, and metathesis properties. It has all three. Iron 3 sulfate has different properties as well. And so by getting more practice with this, we'll be able to better identify, what we kind of expect when we mix these things together and how they react. All right, other questions?
For the ones that aren't on the solubility rules, you said to just kind of look it up to look at results easily. I didn't really get that.
I did a couple of ones that weren't on the solubility chart. There's different things you could do. If something doesn't appear on the solubility chart, you could just look it up in the CRC Handbook of Chemistry and Physics or Wikipedia. The general guideline, if you go back and look at Chem 1A, anything with a solubility higher than 0.1 molar per liter is considered soluble. Anything with a solubility less than 0.1 moles per liter is called insoluble. The data on the CRC Handbook, as well as a lot of the data on the CRC Handbook, has made its way onto Wikipedia. So all that data is, unfortunately, in grams per milliliter or grams per liter. And so we just convert grams into moles, figure out the molarity, see is it above that cutoff or below that cutoff to get the solubility. But there are others. For example, did I talk about the oxides? The oxides are not. Did you remember the solubility rules for the oxides? No, it's not on the chart. And so I might give you an oxide and so you can tell me, is it soluble or insoluble? Right? There's a lot of people who say, hey, that's not fair. You never talked about that, or it's not on the chart, it's not in the book, right? But I think it's fair because you could use your own experience You know, if you have a shiny copper penny and it becomes dull due to oxidation of the metal, can you just wash off the dull brown black coating on the penny? You can't wash it off. Why? Because it's insoluble. And so if you think about metal oxides, let's say you have some rust. Can you just take the hose and just wash off the rust? Maybe a little bit, but it's still there. It's stuck on there. It doesn't dissolve. And so things like rust, copper oxide, those types of things don't wash off. And so you say oxides in general are insoluble. And then you use some patterns. You know, the pattern that I mentioned the other day was, you know, phosphates and carbonates. What do phosphates and carbonates have in common? A high negative charge. Well, what difference is it? Well, it means you have a stronger lattice because of Coulomb's law. Coulomb's law says this: if you double the charge, you're going to double the force holding them together. So in other words, if you double the charge, you double the bond strength. If you double the cation charge, so go from +1 to +2, and you double the anion charge, you quadruple the bond strength, right? Assuming the sizes are the same. And so going from sodium chloride to magnesium oxide, you've just quadrupled the lattice energy, basically. You expect it to be at least 4 times stronger, right? All else being equal. And so a lattice that strong is going to be hard, and so it's hard to break up. And so oxides are going to follow the pattern of the high negative charge, like phosphate, carbonate. Carbonate's -2, but it's a bigger ion than oxide. Oxide is just only a single oxygen. Carbonate is carbon with 3 oxygens and a -2. A carbon with 3 oxygens and a -2, you have the -2 charge dispersed over bigger volume than an oxide. Which one do you think is going to form a stronger lattice, the oxide or the carbonate? We have more chairs somewhere, right there. Actually, you know, my voice, I'm losing my voice. Yeah, I have a microphone here. I've got to remember I don't have to yell. Just in loud. And so you use the patterns here, and you say, well, oxides are probably going to be similar to carbonates and phosphates. Phosphates is 3-, carbonates is 2-, so we'll put them in the same category. You know, phosphates, carbonates, chromates are all insoluble except for group 1 and ammonium. Well, oxides should be all insoluble except for group 1 and ammonium. Now, being able to use these patterns means you would have had to thought about this for a while, because a lot of people, when they get asked the question, and I've asked this question in Chem 1A in an indirect way, I don't ask it directly, I just don't give you the state and you have to tell me the state, what it is. And a lot of people don't get it, that and I've gotten the feedback that that wasn't a fair question, but you know, I thought it was totally fair. All right, so this is what I mean by, you know, some of these you just figure out. Not all. We know sulfides too. Okay, other questions? All right, let's continue where we left off last time. All right, so we're looking at CO2 and water, correct? And what we did was we identified the acid sites and CO2 and the base sites, correct? Did we do the same for water? We identified the acid and base sites in water? Since, this is primarily electrical interactions, then another way of looking at this is, the base sites are going to have the negative charge density, the delta minus. The acid sites have the positive charge density, the delta plus, delta minus here, delta plus, delta minus here. Now, in Lewis acid-base chemistry, we talk about attack. One reagent attacks the other. And by convention, we always say the base attacks the acid. The reason we say the base attacks the acid is, an acid is an electron pair acceptor. And so I guess it could pull an electron pair, which it will. This acid site is going to pull the electron pair. But normally what we say is that the base, let's take water as the base, for example. Water is the base, this electron pair gets pushed into the carbon here, or this base attacks the acid. Okay, that's one possible scenario. We actually have two scenarios because we could have this base on carbon dioxide attack this acid. And so this electron pair attacks this hydrogen here. Now, I want to do a little bit of review of Chem 1A. And so probably the easiest way of looking at these Lewis acid-base reactions is in terms of valence bond theory. In terms of valence bond theory, one of the things we do with Lewis structures is we determine the hybridization on the atoms. And so if we look at the hybridization, what is the hybridization on this carbon here? SP. Did you guys hybridize the terminal atoms or did you leave them unhybridized? Petrucci leaves these terminals unhybridized. I like to hybridize them. And so who's right? Is Petrucci right or am I right? Well, actually neither of us are right because it's somewhere in between, in between there. And in fact, valence bond is not entirely 100% correct, is it? Valence bond theory fails. Do you know the one of the major failures of valence bond theory? O2. And so when we look at O2, well, actually, these are just things. It's not that you have to know this for Chem 1B, but it's so, I'm trying to maybe repeat some of these terms so you don't forget it. Because there's going to be a gap between Chem 1A and organic. In organic, you need to know this, of course, all this stuff. Hybridization is very important in organic chemistry. We don't do as much, but I'll try to incorporate as much as possible. So we got an sp carbon here. I'm going to hybridize the terminals. So if you aren't used to it, it's easy because we just do it the same way. What's the hybridization on this oxygen? sp2. This will be sp2, this will be an sp2. And so when I look at this double bond, the double bond would consist of 1 sigma, 1 pi. And so I'd say the sigma bond is an sp2, sp sigma. Again, an sp2 orbital overlapping with an sp. And the pi bond here is going to be a pp pi bond. Petrucci would have called this a p sp sigma and a pp pi, right? But I'm not. Okay, then these lone pairs are going to be sp2 orbitals, and this is the same. Over here, this oxygen is going to be what hybridization? sp3. So I got a lone pair sp3, lone pair sp3, and then this bond is going to be what? This bond is going to be an sp3 s sigma bond. So good to me. You remember these quite well. That's good. All right. So this is what I'm going to say. I'm going to say this sp3 electrons go here, but there's no room here because can carbon accommodate more? I mean, if this is sp, then I've used up an s, I've used up a p, and then the two unhybridized p orbitals are used in pi bonds. I've got no more valence orbitals. And so carbon cannot accommodate more than an octet. And so what's going to happen is something like this. And so we have two scenarios. I'm going to have the water as the base and the CO2 as the acid, or I could have CO2 as the base and water as the acid. And so we're going to make water the base first. And so this sp3 is pushed in here. And what's going to happen is it's going to break the pi bond. It breaks the pi bond, and these pi electrons end up on oxygen over here. And so what we're going to have is this. Now, this lone pair that's donated is going to form a coordinate covalent bond to the oxygen. We're still going to have one lone pair on this oxygen that was water. And now this double bond gets converted into a single bond. Now we'll have 3 lone pairs here. And so we've lost the pp pi bond, but we look, the hybridization's actually changed here as well. What's the hybridization on this oxygen now? This is sp3. So we converted it from an sp2 to an sp3, and we threw in a lone pair to the sp3 here. And so now this sigma bond is going to be an sp3, sp2 sigma bond. There's no pi bond in here. All this orbital stuff is important when you get into organic, because organic, the structures make all the difference in the world. There's enzymes, and if the atoms aren't correctly positioned, then nothing happens. And so you do quite a bit of valence bond, or more rigorous MO theory to figure these things out. Because when we're breaking bonds, chemical reactions, what do you do in chemical reactions? You break bonds and you form new bonds, right? Well, how do you describe bonds? You're going to describe bonds either using valence bond theory or MO theory, right? And so, if you want to understand chemical reactions, you got to understand bonding. Well, we end up with this. How does this structure look? Well, usually when you get a Lewis structure like this, you look for the octets, and everything has an octet, so it looks good. Does this structure look good to you? If not, then why not? What was that? The formal charges, right? Not only do we look for octet, but we got to look for formal charges. And normally in Lewis structures, we only write the non-zero formal charges. So this oxygen is going to have minus formal charge. This oxygen is going to have plus formal charge. Is that a stable arrangement of formal charge? No, because whenever we make a formal charge, we create what's called a voltage. Like a battery. The battery has a positive end and a negative end. If your battery went dead, and you wanted to create that potential again, that voltage again, then you'd have to separate the charge, right? Separating out the charge, does that require work to do, or? Yeah, in other words, this is one way to envision this formal charge. You have 2 oxygens. They're in a tug of war for electrons. One oxygen wins an electron, the other oxygen loses an electron. So if you have 2 oxygens in a tug of war, one wins, the other loses. Does that sound like a stable scenario to you? No, because oxygen should, if 2 oxygens were in a tug of war, it should end in a tie, right? There shouldn't be a winner, there shouldn't be a loser, it should be a tie, because oxygen has an electronegativity of 3.5. The electronegativity measures the pole of electrons. And so if this is 3.5, this is 3.5, how can this be? This is unstable, right, energetically. This creates a voltage or potential. And this is why we try to get rid of formal charges if it's possible, because formal charges are a result of somebody losing an electron and somebody gaining electrons, usually. But anyway, this is what we end up with. So this doesn't look like a good situation because we got these formal charges. Is this possible or impossible? Well, actually, this is possible because the formal charges that result here, normally we think about electronegativity in terms of Pauling's, but Pauling's is not, Pauling's is a little too general. The electronegativity is going to be dependent on how the atom is bonded. And so if you look at more thorough electronegativity tables, you would have to see, how many bonds there are, how many lone pairs, and that alters its electronegativity. But we aren't going to get into that deep, but this can happen, and this does happen. So we end up with a situation like this, but this is not good. Well, one thing you might remember from Chem 1A is something called delocalization of charge. Is it possible to delocalize this charge a little bit here? This negative charge? It is? How? Yeah, by switching double bonds. We call that, what do you call it again? The double-headed arrow? Call it resonance. Good. And so all we do with this is we redistribute the electrons. And so what we'll do is we'll bring this sp3 electrons into here, make a pi bond, take these pi bonding electrons, bring them out here. And so we end up with this resonance form. And so here we end up with a double bond on the left. Now we got the single bond on the right. And we have this. But it looks as if we just moved the formal charge from the left oxygen to the right oxygen. Now we have the negative on the right side rather than on the left side. But you know something. In reality, does the negative charge jump back and forth between the left and the right? No, in reality, what happens? What's the best representation of this structure? A mixture of the both. The mixture we call a hybrid, right? So are you guys familiar with the hybrid structures, correct? If you were to do the hybrid structure of these two resonance forms, what would the negative charge be on the oxygen? In fact, the bond order, these two bonds are exactly the same, right? It's not a single, it's not a double. What is the bond order? 1.5, right? 1.5. That's good. It's a 1.5 bond. They're exactly the same. And the two oxygens have exactly the same charge. What is the charge on each oxygen in the hybrid structure? Negative a half. Okay. Utama, you're on a roll. It's good. It's a negative a half. Okay, and so in reality, you know, neither of these is correct. We got the hybrid, and the charge on each oxygen is negative 1.5. That's going to help. That's going to help spread out the charge, because the more we can disperse the charge, the less concentrated it is, and the less voltage we have. You know. And so this will help stabilize this ion. This is not an ion because these add up to 0. This will help stabilize the structure a little bit, you know, by what we call delocalization of the negative charge density there. Resonance delocalization helps, especially in things like benzene. Do you recall benzene? And the complete delocalization of the pi electrons there helps make it much more stable than you would expect. Although benzene's been getting some bad news in Porter Ranch. Benzene is also known as carcinogen. But anyway, getting back to this, what we're going to do, and this is what we normally do, when we're doing Lewis acid-base reactions, we ignore the resonance hybrid. I'm going to ignore all the other resonance forms, because this is going to make things easier. And so I kind of ignore this. But I realize that ignoring it's not entirely correct, right? In fact, valence bond is not entirely correct. If I really wanted to do this more correctly, I wouldn't use valence bond theory. What theory would I use? MO theory. Good. Oh. MO theory. In MO theory, you don't have this problem of resonance forms and hybrid. You always end up at the hybrid in MO theory, right? If you go back and look at benzene or whatever else. But for us, what we're going to do is we're going to pick one of the resonance forms, not 100% correct, and then just work with that. Because this is just going to help us. Although it's not that accurate. Well, it's still good though. It's still good because This is what we're going to do. This is not stable, so something has to happen. One thing that can happen is it can just revert back to what it was. But there's another thing that can happen, and that's this. This is not necessary, but this is just helping you remember structures. And so what kind of bond is this here? This would be a sigma bond. What kind of sigma bond? sp2 on carbon to sp3 on oxygen. So this would be sp2, sp3 sigma bond. This is all review, correct? Or is it new for some people? It's all review. If you have an sp2, sp3 sigma bond, then what we have is we have the possibility of free rotation. If you were to rotate, let's say I were to rotate this top oxygen here, would that break the overlap? The sp2, sp3 overlap? No, we're perfectly fine. So about single bonds, there's always free rotation. How about a double bond? If we were to rotate one of these atoms on a double bond, would that break the orbital overlap? Yes. And so there's no free rotation about the double bond because you got the pp pi bonds. And if you start to rotate one of them and not the other, the p orbitals are no longer lined up. You're going to break the bond. And so in order to rotate this, we'd have to break the pi bond. Okay, so what I'm going to do is I'm going to take this and rotate the hydrogen to this side. Even though it's not necessary, I just have a negative charge over here. So I want to rotate this hydrogen so it's closer to this. But in reality, this hydrogen can interact with this oxygen. And why do I care about having it interact with that oxygen? The reason I care about having it interact with that oxygen is this. So this is called a conformation change. A conformation change is when you have some kind of rotation and the atoms rotate to a different position. And so I just take this and spin it and rotate it so that now it's adjacent to this. Here. So what difference does it make? Well, for us, since we're sticking with this single resonance form, the single resonance form has the negative formal charge on this oxygen. There's a positive formal charge on this one. Okay. Now, Pauling's electronegativity works like this. What is oxygen's electronegativity? Oxygen's electronegativity is 3.5. Right? Do you know fluorine's electronegativity? 4. So fluorine has the highest electronegativity at 4. Excuse me. What's the lowest electronegativity? Zero? Negative 4? What's the lowest electronegativity? Does anybody know? See, that's where people get in trouble, because if I said, oh, that has an electronegativity negative 2, then you go, okay. Or would you go, oh, that doesn't sound right? Does it sound okay if something has electronegativity negative 2? How is 0 defined in terms of electronegativity? Does 0 mean it hates electrons and repels them, or does 0 mean there's just no attraction for electrons? So when people are approached with data, they try to reduce the data because this is jumbled numbers. You got a whole bunch of different electronegativities, and what you try to do is reduce it into a simple pattern that you can remember. And so the simple pattern is electronegatives range from, let's say, 0.5 to 4, right? 0.6 to 4. Depends if you want to go radioactive or not. Something like that. What does 0 mean? Those are important things. So I don't expect people to memorize electronegativities, but when you use them a lot, then they come up in your memory. But you should know the range of electronegativities, that kind of thing. Okay. That's the memorization that's useful. Now, let me ask you this. This oxygen has electronegativity 3.5, and this oxygen has electronegativity 3.5. True or false? In other words, fluorine is 4.0. Does that mean fluoride is 4.0 too? If fluorine's 4.0, is fluoride 4.0 on electronegativity? True or false? False. False. Fluorine's a 4.0. Fluoride would be a lot bigger or a lot smaller? A lot smaller. You're right. It'd be a lot smaller. Why? Yeah, you know, you can determine in terms of Z effective. That's fine, but you could do it even simpler. Even simpler is fluoride already has an electron. It doesn't want another electron. You know, because another electron would go into the next shell. No problem. Or Z effective, you know, Z effective with this many electrons is going to be very small. Because Z effective is going to depend on the distances as well. The next electron would be seeing a complete shell. You want to do it by the Z effective. Well, anyway, what do you think? An oxygen with a positive charge, greater than 3.5, less than 3.5, or equal to 3.5 in terms of electronegativity? Greater. This is going to be greater. So if something has a great electronegativity, what it's going to do is it's going to suck electron density from the other species. You've seen oxygen with a positive formal charge. Think hydronium. Hydronium, oxygen has a positive formal charge. What does that do to the hydrogens? It makes the hydrogens much more acidic than water, right? If you look at water, oxygen is 0 formal charge in water. Water, is it very acidic? No. If you look at hydronium, now the oxygen went from a 0 formal charge to a positive formal charge. It sucks the electron density from the hydrogen. So it makes this quite acidic. Well, if this one's quite acidic, what is this? This is quite basic. We have an acid and a base in close proximity here. Now, we got to think about kinetic molecular theory. You know, motion. What are the 3 types of motion? There are only 3 types of motion. What are they? Translational motion. You know, translational is just moving from point A to point B. Translational motion turns out, for you quantum people, it's not quantized, it's continuous. Unless it's confined to a box or an atom, something like that. What else? Vibrational motion. Vibrational motion turns out to be quantized. There's only certain vibrations allowed and forbidden. But anyway, we're going to have vibrations. These bonds are going to be vibrating, whatever the way they vibrate, whatever the loud vibration is. And rotational motion. So there's going to be rotations. And so what we have here is this. This lone pair is in what orbital? Well, what's the hybridization of this oxygen? sp3. So we got an sp3 lone pair, and this bond is on S on hydrogen, overlapping with a sp3 on oxygen. And so we're going to have one sp3 orbital come in to the S. It's going to kick the other sp3 electrons out. And so these sp3 electrons come in to the s orbital here. These electrons get kicked out. And so one sp3 comes in, the other sp3 gets kicked out. And so what we have here is an acid-base reaction, a proton transfer. But this proton transfer happens within the same molecule. And so this is what we call an intra or intermolecular proton transfer. Intramolecular proton transfer or intermolecular proton transfer? Intra. And so this is an example of an intramolecular proton transfer. Intramolecular proton transfers aren't as rare as you might think. They're quite actually pretty common. And so here we have an intramolecular proton transfer. Proton transfer happens within the same molecule. So that happens, and we end up with this. I'm not drawing these with the proper geometry because SB2 this should be a trigonal planar. I didn't make it. I made mine more T-shaped. But the Lewis structures, you don't have to worry about this too much, unless you're trying to draw it, more accurately. And so that lone pair gets stuck on this. For this. All right, everything has an octet here. How are the formal charges on this species? Are there any formal charges? Normally we only write the non-zero formal charges. There are no non-zero formal charges. All the formal charges are 0. And so this structure looks good. This structure looks good. So, actually, do you recognize this molecule? It's H2CO3. H2CO3 is carbonic acid. So if you take CO2 and water, mix them together, you're going to form a little bit of carbonic acid. This is a Lewis acid-base reaction. This is why we call CO2 acidic. And this is going to lower the pH of the water. In fact, when you do your acid-base titration, you expect the pink color of phenolphthalein to fade over time. Eventually, it'll go colorless again. And what's the reason? Why does the light pink color at the end of a titration eventually go colorless again? It's because there's CO2 and air. And the CO2 will reacidify the water, making the pink color fade in the titration. If you want that pink color to fade immediately, you take a straw and blow bubbles. If you blow bubbles in that, the pink color is gone right away because it's saturated with CO2. But you also memorized something. What did you memorize about carbonic acid? Is carbonic acid stable? No, carbonic acid spontaneously decomposes back into CO2 and water. In fact, CO2 and water is more stable than this. And that's just from memorization. And so what happens is just a little bit of carbonic acid is formed. It's not like every molecule of CO2 is converted into carbon. No, just a tiny fraction of them are. And they can easily decompose. But since we got CO2 present always, it can reform. And so this is one of the reasons why our DI water, do you know what the pH of our DI water is? DI stands for distilled or deionized. Let me clear that up right away. No. This is not distilled water. Distilled water is quite a bit more expensive. Distilled water should be pH 7, but our deionized water is not. It's because of how we store it. The deionized water is just processed tap water, and then it's stored in a big tank up there. The big tank is exposed to air. Air contains CO2. The CO2 gets in our DI water and changes the pH. If you took a pH meter, did you guys do this last semester, Chem 1A? If you take a pH meter and measure, do you guys remember, Vaughn, you remember the pH of the water? Utima, you remember the pH of the water? No. pH of our DI water is 5.5. 5.5, that's really acidic, isn't it? It's because of the CO2. And so, what you probably did in Chem 1A is you measured the pH of boiled water. Why did they boil it? They boiled the water to drive out the CO2 gas, get the pH closer to 7. Because if you drive out the CO2 gas by boiling it, then we destroy more of this carbonic acid as this goes backwards. All right, now we think about driving forces. In acid-base reactions, we think about going from, stronger acid, stronger base to weaker acid, weaker base. Well, what's happening here? When we're comparing the acids, the two acids, CO2 is the acid over there, what's the acid over here? Because CO2 was the acid, wasn't it? And water was the base. So here's our acid, here's our base. Well, what's the acid base over here? It turns out carbonic acid is both the acid and the base. And going backwards here. And so we think, well, that's so tricky. I'd rather think of it in other ways. Well, thinking in other ways, we might think in terms of bonds, Because when we're talking about driving force, we want to go from less stable to more stable. More stable species should have stronger bonds. Less stable species should have weaker bonds. And so we can do something back in chapter 10, that is, we sum up all the bond energies of the reactants and compare it to the sum of the bond energies of the products and see which side has stronger bonds, which side has greater bond energies. And that might tell us why CO2 and water is favored. But anyway, even though you memorize this, it's kind of hard to predict, If you didn't memorize that carbonic acid's unstable, well, what's the driving force here? It's tricky, isn't it? Well, that was with CO2 acting as an acid, but can CO2 act as the base as well? And so let's, because water's amphoteric, so we know water for sure can act either way. And so let's have CO2 act as the base. Floor. All right, let's redo this. When we have chemical reactions, these things are in motion. There's translational motion, right? And so we get collisions. And so both reactions can occur, CO2 acting as the acid and CO2 acting as the base. And so we should check for this possibility as well. If CO2 acts as the base, then it's going to attack the water being the acid. And so Lewis base is electron pair donor. So this sp2 lone pair is going to get pushed into the s orbital, which is going to kick these sp3 electrons out. Does that make sense? Or sp3 electrons into the sp3 orbital. So we end up with this structure here. I'm going to just take this and bond it with a hydrogen. What else do we got? Is that it? Yeah. That's it. And hydroxide. So here we got the negative charge, formal charge on oxygen over here. And over here we've got a positive formal charge on this oxygen here. All the others are 0. So we get charges that result here. So one way to get rid of the formal charge is just to go backwards, right? You have this attack that hydrogen and give the electrons back to the oxygen. Just go backwards. But is there another route that we can go? So we got hydroxide ion here and then this weird cation. What can we do with this here? Can we get rid of that formal charge? We can try. Maybe we could try to rearrange the electrons. So let's try to do that. And so what I'll do is I'm going to drop these into the bond. So this sv2 is going to be converted into a bond here. So this lone pair gets converted into bond. And that means there are too many. If I get a triple bond here, I can't have a double bond here. So I'm going to kick a pair out here. And so we generate this. What do you call this? I'll just rearrange it a little bit. So now this oxygen went from a positive formal charge to a 0 formal charge. But you look at this oxygen over here, this oxygen is now a positive formal charge. And so one thing that could help stabilize this is this. This is called, what do we call this? Spreading out the charge. Called delocalization. And when we have delocalization due to resonance forms, we call this resonance delocalization. However, these two resonance forms are not equal, right, in terms of energy. When you did resonance delocalization for carbonate, you generate 3 equivalent resonance forms, you know. When we do it for this, and these are unequivalent, but it's okay because it still helps spread out that positive charge. The more we can spread out that charge, the more stable the ion is. The more the charge is concentrated, the less stable it is, the more reactive it is. And so this will help, but you know, it really doesn't get rid of it. And so is there something else we could do to help? I don't know, maybe what we can do is we can lose this hydrogen as a proton. So if these electrons get sucked into the oxygen and make a lone pair, then we'll end up with an H+. But if we end up with an H+ out here and we have a hydroxide here, H+ and hydroxide just make water and we're back to where we started. And so is there some other way we can break bonds and form bonds to come up with a new product that's somewhat stable? And the answer is no. You know, no matter what I try, this ends up as a dead end. And so this particular collision doesn't result in anything. You know, if we form this, it's going to quickly revert back. And so the only reaction that we had was when CO2 acted as the acid. So oftentimes people think of this. And so you come up with this. In Chem 1A, at the end of I think chapter 9 or chapter 10, they say that non-metal oxides are acidic. Have you heard that? This is in periodic trends. Non-metal oxides are acidic. Metal oxides are basic. And semi-metal oxides are, this wasn't at the end of the chapter, but I want to see if you can figure it out. Metal oxides, basic. Non-metal oxides, acidic. And semi-metal oxides will be not neutral. Semi-metal oxides will be amphoteric. And so semi-metal oxides are the amphoteric oxides here. Like, and this is one of the interesting things about antimony or whatever, aluminum, silicon, those oxides. All right, I'm going to stop here. We'll take a break, and then we'll look at a metal oxide next.